to the energy physics group of Santa Maria. It is a real pleasure to have this opportunity to give this talk to you. I hope that I have the opportunity to be in person at Santa Maria in Valparaíso at some point in the near future. Okay, today I will talk about this about radiative seesaw models, in particular scotogenic model, which is realized at the tree loop level. First, let me just put this full screen. I think this is better. So
I see. Fine.
Okay. Okay, and the motivation for this standard model, for physics beyond the standard model in general, is that, as we know, the standard model is incomplete. So the standard model is complete in this is a complete theory in the sense that all of its fundamental predictions and particles have been detected. And it has been tested over the last decades exhaustively, and it's a so precise theory that it's very hard to spot how we should go beyond that. But we know that we must replace the standard model by some theory more complete, because the standard model leaves many answers without many questions without a satisfactory answer. There are many motivations, many problems, open problems in the standard model. I select here just two, which are two of the main motivations to go beyond the standard model: neutrino masses and dark matter. And also I will explore this kind of new physics in the sequence of this presentation. So we know from cosmological and astrophysical evidences that there are an amount of matter in the universe, around 25% of the energy budget in the universe is made of a kind of matter which we don't know what is its nature. We can only infer its existence by gravitational effects, such as galaxy rotation curves, imprints in the cosmic microwave background, and other kinds of observations. And there is no particle in the standard model which can account for this dark matter. Neutrinos could in principle be a good dark matter candidate, but they turn out to be too light. So they are what is called a hot dark matter candidate. And it actually makes up a few percentage of the dark matter abundance, but it cannot account for the full abundance that the observations indicate today. So considering the neutrinos themselves, the standard model was built under the assumption that they are massless. But now we know that by means of the oscillation experiments, that they actually have a mass. We have plenty of evidence from oscillation experiments with solar neutrinos, atmospheric, accelerator neutrinos, and so on, which firmly establish that neutrinos do have a mass, although this is a very, very small. We don't know the absolute mass scale of the neutrinos, but it is constrained by some direct measurements for neutrino masses and from cosmological arguments. These masses should be smaller than around 0.1 electron volts. And this is definitely physics beyond the standard model. And in my opinion, the existence of neutrino masses is the main motivation to extend the standard model. But you may wonder, why don't we give neutrino masses just in the same way that we give the other fermions their masses via electroweak symmetry breaking? Of course, you can do that. It goes as follows. You include right-handed neutrinos, and these right-handed neutrinos will pair the left-handed neutrinos via the Higgs boson, and after electroweak symmetry breaking, a direct mass term will arise, and this mass will depend on the vacuum expectation value of the Higgs field and the Yukawa coupling. So to account for a mass of order 0.1 electron volts, this Yukawa coupling should be of order 10 to the minus 12. So this is a very small number. This is even smaller than the QCD angle, the theta QCD, which motivates which is the origin of the so-called strong CP problem, which is a fine-tuning problem of the standard model that motivates the axial models and so on. This Yukawa coupling is even smaller than that. So it doesn't seem much satisfactory explanation. If you look at, I like this plot, which shows the masses of the standard model fermions in this logarithmic scale. For the charged fermions, you can see that they are more or less clustered around, we cannot say the same scale because there is a lot of variation from the top mass, for instance, to the electron mass. There are several orders of magnitude. But if you look at neutrinos, neutrinos are separated by a big gap of more than 6 orders of magnitude to the electron mass. So the neutrinos really seem to be, the origin of neutrino masses seem to be different from the other model fermions. And not only that, if you insist with this naive attempt to generate neutrino masses, including the right-handed neutrino fields, there is no reason why you should not include a term like this, a Myron-Emerge term for the right-handed neutrinos, because they are singlets under all the gauge symmetries of the standard model. So, and this is the kind of thing that happens only with neutrinos. No other fermion can have a term like this. So you see that including right-handed neutrinos is a non-trivial modification of the standard model. Okay. So all of this seems to be trying to tell us that there are some new mechanisms, some new physics that operates behind the generation of neutrino masses. So of course, over the years, many theoretical proposals have been put forward to try to give a plausible explanation for the smallness of the neutrino masses, and we arrive at the seesaw mechanism. So A long time ago, Weinberg wrote down this dimension 5 operator. The only dimension 5 operator you can build with the standard model field content and symmetries, and it generates neutrino masses. Then it was realized that this operator, this blob here, can be realized in a couple of ways. At tree level, there are precisely three ways of in which this operator can be realized. And this gives rise to the well-known type 1, 2, and 3 seesaw mechanisms. So you can include new singlet fermions like this, and you have type 1 seesaw, or a triplet scalar for the type 2 seesaw, or a triplet of fermions. In all of these tree-level seesaw, we have that the smallness of the neutrino masses is connected to a very high scale. As you can see here, if you put this coefficient, which could be, for instance, the Yukawa coupling in this type 1 seesaw, if you say this coupling is of order 1, for instance, this high energy scale, which would represent the mass of the right-handed neutrinos, should be very high, close to the gut scale. Similarly, occurs for the other two mechanisms. And although these models are very elegant and appealing, one of them might be the correct answer for the origin of the neutrino masses, but they are very hard to test because either they require a very large mass scale, or if you, which implies that these particles are too heavy to be produced at colliders or other kind of probe, or if you say that this mass scale is lower, you have to suppress these couplings. So you end up with a very weakly coupled particle, which is very difficult to probe.
Tessio, if you like, I could comment at this point, not waiting for the end of the seminar. The point which is advocated by Jose Vavier, who proposed the type 2 seesaw. According to him, well, but and I share this opinion. This seesaw does not require too high scale, because this upper vertex is the lepton number violating vertex, and characterized by a dimension full parameter. So
yes,
then this scale, this factor of Weinberg operator, C over lambda, could be it is in this diagram would be mu parameter, this trilinear parameter, over mass of delta squared, and mu parameter is technically natural to be very, very, very small, because in the limit of mu tends to 0, the lepton number symmetry is restored. So then it is thought natural, and in this case delta should not be very, very heavy. This is a comment.
Well, thanks, Sergey. Yeah, that's right. And in this case, it's kind of natural to have this mu parameter. Okay, you have the mass parameter for the triplet that appears in the potential.
Not very high.
Yeah, not very high, but
not very
it's
heavy.
still it has to be at some high scale, not too high like in type 1 seesaw, for instance.
Sure. At
And
the TV in the TV ballpark.
yeah. And also Jose Valle also advocates that this should be called the type 1 seesaw, actually, because he considers this the simplest seesaw realization for many regions. And yeah, but you're right. Okay, so the same Weinberg operator can be realized also at loop level. And over the years, there have been many proposals. One of the first proposals was actually the Z-bubble model, which is a two-loop realization of the Weinberg operator. In the 80s, then in 2006, it was proposed by Ernst Mayr, this one-loop model, the scotogenic model, which came to be very famous. And I will say more words about this model in this sequence. But the idea of these relative seesaw models is that the neutrinos are actually massless at 2 levels, and they get their masses only via these diagrams, and you have suppression because they are generated via loop. So if you have an n-loop diagram generating a neutrino mass, this mass will be suppressed by a factor of 1/16 pi square for each loop you include in the mass generation. So in this way, you can suppress the neutrino masses without having to suppress much the couplings in your model, not appealing for very, very high energy scales for the this should be the scale of breaking of lepton number. And the interesting thing about these models is that in general, with this natural suppression given by the loops, the masses and couplings are such that these models are very much testable. They predict particles in a mass range that can be in reach of current experiments. So that's a very nice feature. I'm looking now that I wrote here 3-level seesaw, but this is vegetative seesaw mechanism. So this kind of model is interesting in this sense, because the whole idea is plausible. Neutrino masses are small because are generated via loop, and the models are in general quite have an interesting phenomenology. So this is the outline of the rest of the talk. I just finished the introduction, and in the sequence I will talk about the scotogenic model, which I just mentioned, and then focus on a specific realization of the scotogenic model at 3-loop level, and then give some more details about its phenomenology, like neutrinoless double beta decay, precision electroweak observables, lepton flavor violation, and dark matter. So the scotogenic model. So this model was first proposed by Ernst Mayr, and it's a very simple construction. So here's the particle content of the extra fields that you include. It is an scalar inert doublet and right-handed neutrinos. So you include these two fields and an extra discrete symmetry under which these fields are odd, while all the other standard model particles are even. So with this field content, in the lepton sector, you have a Majorana term for the right-handed neutrinos and a Yukawa interaction. But first notice that actually these fields in R are not, strictly speaking, are not right-handed neutrinos because they will not pair up with these left-handed neutrinos. This is not the Higgs field. This field will not acquire a VAV. So there is no mixing between these NR fields and the left-handed neutrinos. But I will keep calling it right-handed neutrinos anyway, but please understand what I mean. You can call it heavy neutral leptons or anything else. By force of habit, I call it right-handed neutrinos. And these two terms only are not enough to guarantee the violation of lepton number, because you could, for instance, assign a charge for the eta field, a generalized lepton number charge of 1, and say that NR is neutral. So these two fields will not, these two terms will not violate lepton number. But in the scalar sector, there will be this coupling, and this will necessarily violate, there is no possible definition of lepton number in presence of this term. So these three terms are required in order to have lepton number broken by two units, and thus to generate neutrino masses. And it is realized like this. With this term, you have the Yukawa term, you have this coupling, and the scalar one allows you to close the loop. And as you can see, the neutrino masses will actually depend on lambda 5, which is this term which breaks lepton number. If it goes to 0, neutrino masses also goes to 0 because lepton number is restored. It will depend, of course, on a loop function and on the Yukawa couplings and the mass of the right-handed neutrinos. So in this model, this symmetry, which forbids the three-level direct mass term for the neutrinos, and there are also the purposes for this symmetry, for instance, avoiding flavor change in neutral currents, the scalar sector. But this symmetry will remain unbroken because eta does not develop a vacuum expectation value. And so the lightest charged particle under this symmetry will remain absolutely stable. And if this is a neutral particle, it is a good dark matter candidate. So the same symmetry, which is responsible for the generation of neutrino masses at the loop level, is also responsible by the stability of dark matter. So in this construction, you have a clear connection between the origin of neutrino masses and the dark matter particles. The dark matter particles are running inside the loop that generate neutrino masses. That's why this model is called the scotogenic. Scotus means dark, and genic generation. So it's a dark generation of neutrino masses. And that's why this model became very popular, because it connects neutrino masses and dark matter in a very simple setup. So you can see that with this very simple setup, you achieve a lot. You account for neutrino masses, you have a good dark matter candidate, you only included 2 new fields and 1 extra symmetry. And besides that, this model has a very rich phenomenology. But such a simplicity has a price, which is, for instance, if you look at the lambda 5 parameter, you make a quick estimation based on this expression in order to get the correct order for neutrino masses. You can see that if you assume the right-handed neutrino masses at the TV and you call couplings of order 0.1, for instance, you have to impose a value of 10 to the minus 8 for lambda 5. And this is a very small number. Okay, but we have to impose this in order to generate the correct neutrino masses. Conversely, you can also say that if lambda 5 is sort of natural with a number close to 1, then you have to suppress the Yukawa couplings. So you should have Yukawas of order 10 to the minus something, 10 to the minus 6 or so on. And this is, it would be nice if we could avoid altogether these very small numbers. And this is a motivation to modify the original proposal in order to give a more natural range of values for these parameters. Before I go to the actual model, let me just point out that from this original proposal of this scotogenic model, there are many variations now of the scotogenic model, changing, for instance, here in the loop, we have a singlet fermion. You can extend this with a higher multiplet under SU2. You can put here other multiplets also for the scalars. And today in the literature, there are plenty of variations of this original scotogenic proposal. And all of them with different phenomenologies, which are interesting. Here, we are going to focus in a variation of this scotogenic model, which tries to first increase the suppression in the generation of neutrino masses, because it will be generated at true loop level. And okay, we could propose many possible topologies for the neutrino masses at true loop, but we are guided by this, looking at this small value of lambda 5. Let's try to generate this lambda 5 at loop level. So explain dynamically why this lambda 5 should be small. So this is one of the motivations for this work, which was done in collaboration with some people here in the audience, Antonio Carcamo, Sergei Kovalenko, and also Asma Abada, Nicolas Bernal, and Takashi Toma. So this is the particle content of the model. We have here the standard model fields, and the extra fields in the last columns are the fields that already are present in the scotogenic model, the right-handed neutrino and the inert doublet. And we also include 4 new scalar singlet fields. Okay. So here we have the symmetries of the standard model, the gauge symmetries. And besides these symmetries, we impose the Z2 symmetry, which was already present in the scotogenic model, and also U1 prime global symmetry. So the Z2 symmetry will be important to forbid the direct mass term for the neutrinos. So there is no 3-level mass for the neutrinos because of Z2. Notice that all the standard model fields are even, and the extra particles are all odd except the sigma field, which is even. And this sigma field will be responsible for the breaking of this global symmetry. We assume this breaking occurs at the TV scale, but as this sigma is even under Z2, Z2 will not be spontaneously broken. It will remain intact, and it will be responsible ultimately for the stability of dark matter. So this symmetry avoids these terms. The E1 prime will forbid now this lambda 5 term, which is if present would allow to close the loop at one loop level. So without this term, we need more loops in order to have a closed diagram. And the charge assignment is such that we achieve this at the 3-loop level. And then there will be another term, the scalar potential, which together with the Yukawa couplings and Majorana mass term will break lepton number by 2 units. This trilinear term here. So with this field content and symmetries, this is the lowest order diagram we can have for neutrino masses. From this, we can compute the masses for the neutrinos. I'm showing here the formula. It's not very illuminating, but I just wanted to point out that we, this way, okay, the masses will depend, of course, on the Yukawa couplings and on a function that depends on the loop, and all the particles inside the loop, their masses and mixing angles going to the physical basis, all of this will get inside the expression for the neutrino masses. So all these 3 parameters will be connected to the neutrino masses directly. And one thing, we are considering only 2 generations of right-handed neutrinos for simplicity, to have a more economical setup. And this implies that one of the light neutrinos will be massless, okay? And this is verified by this expression. And also notice that in the limit of sine of theta going to 0, this theta phi angle here, in this limit, lepton number is restored. So neutrino masses would be 0 in this case. Just to mention that this term is this sine of theta depends on this a parameter here, okay, which is the lepton number breaking parameter. Okay, so let me now talk about some phenomenological consequences of this setup. First, neutrinoless double beta decay. As we have Majorana neutrinos, of course, we have this connection with neutrinoless double beta decay, which is only possible if you have Majorana fields. Okay. In this case, we have right-handed neutrinos. We could, in principle, contribute to this process. However, the Z2 symmetry forbids the mixing between the right-handed neutrinos and the active neutrinos. So they end up not contributing to the neutrinoless double beta decay observable, which is the so-called Majorana effective mass. So this mass enters here in the diagram. The whole amplitude will be proportional to it, and the experiments typically constrain this quantity. So in our case, as the right-handed neutrinos do not contribute, and also we have one massless neutrino, that means that this observable will depend only on the other masses, non-zero masses of the active neutrinos, which are defined by the oscillation experiments, and also on the Majorana phases in the PMNS matrix. So if we assume that the phases are zero, we get definitive predictions for this observable, which will depend on the hierarchy of neutrino masses. If neutrino mass ordering is the normal one, this observable would have a value of around 3 milli-electron volts. And in the case of inverted hierarchy, ME would be around 48 milli-electron volts. These values correspond to the maximum possible values for these expressions, which occurs when the phases are set to zero. If we allow these phases to vary, there can be cancellations, and we can have some smaller values for ME. This is shown in this plot here. So the maximum values in the previous slide for the inverted hierarchy is here, for the normal hierarchy is here, and there is a region which is allowed depending on the lightest neutrino mass and depending on the Majorana phases. So you have a whole region which is possible for neutrinoless double beta decay. In our case, as the lightest neutrino is massless, in our model we live at the y-axis. So the allowed values for ME in our model is just a band here for the inverted hierarchy with the maximum value of 48 milli-electron volts, and another band for if the normal hierarchy with a maximum value of 3 milli-electron volts. Unfortunately, in this plot, I didn't put the bounds. The strongest bound currently comes from Camelan Zen, which is around 60 milli-electron volts. It is more or less here. So from here, everything which is above this region is excluded, but the current experiments still doesn't touch the regions for neither for inverted hierarchy nor normal hierarchy. But the near future experiments can probe these regions. And for instance, the Nexo experiment can reach a mass of around 10 milli-electron volts. So the inverted hierarchy scenario will be probed in the next generation of neutrinoless double decay experiments. And if we have a positive signal from one of these experiments, that would mean in our model that the inverted hierarchy is to be preferred. In case of normal hierarchy, it is not in reach of next generation of experiments. We need to improve the precision even further to probe this region here in the normal hierarchy scenario. Okay. So jumping to precision electroweak observables, we have new particles which contribute, we give deviations for the oblique parameters as to u, because some of the scalars come from the inner doublet, and as we have new SU2 multiplets, non-trivial multiplets, these affect these parameters, which will depend on these loop functions pi here, that depends on the masses and mixing angles of the scalar sector. And recently, the CDF collaboration reported a measurement of the W mass, W boson mass, which is not in agreement with the prediction of the standard model. So their value deviates from the standard model from over 7 sigma. It's a 7 sigma discrepancy, the so-called CDF anomaly. And okay, this anomaly has yet to be confirmed by other experiments. We need to wait to see how this will unfold. But if this is really a genuine signal, we know what kind of new physics could be the source of it, because the W mass is affected by the corrections in the STU parameters. So they STU enter in the W mass according to this expression. The standard model prediction for STU is 0. So in the standard model, this whole part is 0. So you have, of course, the W mass is the standard model prediction of 80.37 GeV. However, in presence of new physics that contribute to STU, the value of the W mass should deviate. But the thing is, if you change the STU parameters, you not only change the W mass, you change many other precisely measured observables like the Z boson mass, the Fermi constant, the fine structure constant, and so on. All those observables which are dependent on the STU will be affected if you cause a shift on them. So in order to account properly for this new measurement by the CDF collaboration, you have to take into account all these other parameters in order to not mess them up. And you have to make a fit including all these parameters and the measurements of them independently, and including on them the measurement of the CDF. And this has been done, for instance, in this reference, after the publication of the anomaly by the CDF collaboration. And the result of this global fit is that the new set of parameters that you should have when you include the CDF measurement deviates a lot from zero. If you look at the PDG before the measurement of CDF, you can see that these values are all around zero, all consistent with zero, which is the standard model prediction. But with the CDF measurement included, these parameters deviate a lot from zero, and we, using this fit, we can find a region of parameter space in our model which account for these values of STU. So this is shown in these plots here. So the STU parameters will depend mostly on the charged scale mass and phi 1 and phi 2, because they come from the mixing from the inert doublet scalar. And these parameters are very sensitive to the splitting of these masses. So basically, they will constrain the splittings. So here I'm showing the splitting between the phi 1 and the charged scalar as a function of the charged scalar mass. I'm assuming that this mass is in the TV range. And as you can see here, we can explain the W mass anomaly within 1 sigma or 2 sigma, provided that the splitting is not too large. So we need splittings of order of a few hundred of GeV. So for instance, if this charged scalar is 4 TeV, M phi 1 should be at most 4.3 TeV, and so on. So small splittings. If you change, of course, this will depend also on the other scalar mass, and if you change this mass, the region will change accordingly. But anyway, you really need splittings not larger than a few hundred GeV, 300 GeV, for instance. Another kind of experiment which is very important to probe our model are experiments that look for processes of lepton flavor violation. So these kind of processes are very important because in the standard model, lepton flavor is strictly conserved, at least at the perturbative level, because of the lepton number symmetry. So any observation of flavor changing process in the lepton sector would be a clear indication of physics beyond the standard model. And in our model, this kind of process is directly connected to the neutrino mass generation, because the same kind of diagram that generates the neutrino masses, if we put here the neutrinos instead of the charged leptons and change here the scalars, forget about the photon. If you remember, this is just the scotogenic diagram that generates the neutrino masses. But by SU2 symmetry, if that diagram exists, this diagram should exist as well. And in our case, will be modified because we have a tree loop diagram, but the processes of charged lepton flow evaluation can occur at one loop level. And they will be mediated by the charged scalar eta and by the right-handed neutrinos. So here I'm showing some of the processes that have been measured concerning these flow evaluating processes. Several experiments are searching for these processes. Mainly the variative decays of the muon and the taus. The most stringent bounds comes from the muon processes, mainly mu3 gamma, which has the stringent constraint so far by the mega experiment, which constrains this branching ratio to be smaller than 10 to the 13. Other processes like mu3e have a bit weaker constraint, and there is also the conversion ratio of muons to electrons in the presence of atomic nuclei. These are less constrained today. But the interesting thing about this experiment, these experiments, is that they will have a significant improvement in their sensitivity in the near future. For instance, in mu3 gamma, we expect an improvement of almost 2 orders of magnitude, while for mu3, we can have an improvement of 4 orders of magnitude, which is a remarkable improvement. And more remarkable yet, the improvement in the mu3 conversion, which can improve by 6 orders of magnitude. So these future generation experiments will be very important to test the kind of physics that we have in this variative seesaw model. So we apply the current constraints on this parameter space of this model. First, from mu3 gamma, we can see that the local couplings are constrained to be below more or less 0.1. If you increase the mass of the charged scalar, this value can be a bit higher, but it is a strong constraint. We have a similar constraint from mu3, even though the experimental precision in this channel is not so large as the mu3 gamma. In this model, we have an enhancement because besides this diagram that contributes to both mu3 and mu3 gamma, we have also this box contribution, which goes like the Yukawa couplings to the 4th power, while this goes like the Yukawa to the 2nd power. So these diagrams tend to be enhanced if we have large Yukawa values. And as we are concerned specifically with this large Yukawa coupling regime, because we don't have to suppress them because the neutrino masses are generated at free loop. So we can have that high Yukawa couplings. These diagrams cannot be neglected. And you can see the effect of them here in this region, which is more constraining compared to the mu3 gamma case, which goes up. I forgot to mention all these white regions here are excluded. So we have a very strong bound from mu3e. And once we have an idea of the parameters of the order of magnitude, which would be compatible with the experiments. We do a detailed scan on the parameter space of the model. We make use of parametrization so that all the points in the scan will automatically fulfill the neutrino oscillation data. And then we scan randomly the other three parameters, assuming the masses are at the TV range and the couplings are neutral, in the sense they are close to 1. So here is what we get. In this plot, I'm showing the branching ratios for the Neutri process, mu conversion in nuclei. And in the color is the intensity of the branching of mu-trigamma process. So first notice that these regions here are the excluded regions. So we have a lot of points excluded by mu3e, and also by mu-trigamma. These yellow points here are also excluded by mu-trigamma. But there are many points which pass this bound, and besides that are in reach of future sensitivities for these experiments. This, in particular, this mu conversion, which currently doesn't exclude almost anything. This kind of experiment will be able to probe many significant part of parameter space of the model. And even more, the Neutri channel will be a very strong probe for our model. Okay? So we have a large portion of the parameter space of the model that can be observable in the next generation of the lepton flare violating experiments, and this is exciting. So going back to that region that can explain the W mass anomaly, from this region we can choose a point which explains the W anomaly, and let's see where this point lies in the scan. And we can see that it is here. It evades the current bounds, and besides that, it provides a signal to mu3e experiments, to mu conversion experiments, and if you look closely here, also to mu-trigamma experiment. So, for instance, looking at this benchmark point, I have that this model in this point explain the W mass anomaly. It accounts correctly for the neutrino masses and mixing parameters, accounts for dark matter, as I will talk in a minute, and besides that provides visible signatures in the future experiments. And this is a very nice feature of this kind of model, of this model in particular. Its phenomenology is very rich, as you can see. And here is another example. I can take another point and I have visible signatures, okay? And also, this was considered in normal hierarchy of neutrino masses, and I can also have basically the same thing if the inverted hierarchy is the correct part. Okay, I'm not sure how am I going concerning the time, Antonio. Do I have some time?
There is some flexibility, Tessio.
Okay, so But yeah, I'm close to finish. The last thing I wanted to comment is regarding the dark matter phenomenology. We have in this model plenty of room to accommodate a successful dark matter candidate. It can be either a fermionic dark matter or an scalar dark matter. They will be stabilized by the preserved Z2 symmetry. So I'll just outline the phenomenology of dark matter here, because we will not commit to any particular scenario because there are many possible scenarios, but the phenomenology follows the same lines of the scotogenic model, for instance. It's very similar. So if we consider a fermionic dark matter candidate, this will be right-handed neutrino, and this right-handed neutrino will be produced only via Yukawa interactions. Okay, so it will annihilate the early universe via T-channel into charged leptons or active neutrinos via the exchange of one of the scalars of the inner doublet. So this cross-section goes like the Yukawas to the fourth power, and if you compute the Wellek density, it will require that these Yukawas are of order 1. So if you remember this plot, Yukawas of order 1 are not so simple to achieve because of the strong bounds from charged lepton flavor violation. So at first sight, it would seem that fermionic dark matter is not possible. However, notice here that this plot is somewhat simplified because we are assuming that all the Yukawas are the same in this plot, but in reality, they are not the same. There are several Yukawas. The Yukawa that couples the electron to the electron, the mu, and the tau to the right-handed neutrinos. And by exploiting these, you can achieve the correct probability abundance, like as computed in this reference, for instance. You can see here points in which the correct dark matter is achieved. And you can see that most of the points, the blue points, you have the Yukawa, the tau Yukawa. The tau Yukawa can be close to 1. And this is okay because the current constraints from lepton flavor violation on the tau decays are not so stringent. So by means of this Yukawa coupling, you can have a successful annihilation of the dark matter. And the other Yukawas, the mu and the electron Yukawas, can be smaller. And this is no problem because you compensate this by a larger tau Yukawa column. So in this way, you can have a correct Wellek density for dark matter. And concerning direct detection, as the right-handed neutrinos doesn't couple to quarks at true level, and basically there is no constraint from direct detection. There are, okay, it was computed in this reference. The bounds coming from loop processes, but the bounds are very weak. So the basic requirement is really satisfying the Wellek density and avoid the charged lepton flavor violation constraints. Okay. In the case of a scalar dark matter candidate, the lightest scalar will be a mixing one of these scalars, and there will be a mixing between the scalars of the inner doublet and the singlet states. So in this case, the dark matter interactions are gauge or scalar interactions. They are not related to the Yukawa coupling, so there is no correlation with lepton flavor violation. So the scenario is much less constrained compared to the fermionic scenario. And here we have this scenario in which, depending on the mixing angle, you can have a dominant a component which is predominantly from a doublet, or a component that is mostly singlet. So the phenomenology will depend a lot on this specific mixing, because if it is predominantly a doublet, the main annihilation channels will be via gauge interaction, and the dark matter candidate will have properties similar to the inert scalar dark matter model. However, if it is mostly singlet, the annihilation channels will be via mostly Higgs boson, and the scenario is like a Higgs portal dark matter. Okay, so I'm showing here just an example from this recent reference by Marco Aurelio, Giovanna, Cotin, and Ivania, which studied this scenario of dark matter from an inert Higgs doublet. And you can see that the relic density can be achieved for masses above some few hundreds of GeV. And most of these points pass the current direct detection limits. So again, in our case, we would have an intermediate case between this and the Higgs portal scenario. But anyway, there would be no problem to accommodate a dark matter candidate here. Okay. Okay, so I think I'm extrapolating the time, so that I arrive at my conclusions. So radiative system models are very well motivated extensions of the standard model, and they give a plausible explanation for why the neutrino masses are so small, and they present a very rich phenomenology. We have constructed a scotogenic model in which neutrino masses are generated at the true loop level, which allows us to have particles at the TV scale and no fine-tuning in any of the parameters. We can accommodate easily either a fermionic or a scalar dark matter candidate, whose stability is ensured by the preserved symmetry. And the model is able to explain the double mass anomaly while satisfying all constraints from neutrinoless double beta decay, charged lepton flavor violation, electroweak precision observables, and also provides invisible signals that can be proved in future experiments. So that's all I had to say. And thank you very much for your attention.
Thank you very much, Tessio, for the very nice and complete seminar. Question from the audience?
Another question.
Yes.
I think the model is very important to have one massless neutrino, right?
Yes.
Well, I am surprised that this is not ruled out by experiment or by other things, like, for example, beta decay itself or other things. I mean, it seems very unnatural, if you want, for one thing.
Yeah. This is a possibility. This is a viable possibility. For instance, the neutrino oscillation experiments constrain only the mass differences among the light neutrinos, and but it doesn't tell anything about the absolute mass scale. So this experiment does not constrain at all the how light the lightest neutrino can be, for instance, and if it's zero, it's perfectly okay. And other experiments are not very sensitive to this very small mass because, for instance, if you think of neutrinoless double decay, for example, okay, one of the electrons, one of the neutrinos is massless, but the other masses, I mean, the observable in the end of the day will not be affected, will not be enhanced by this masslessness of the lightest neutrino. So yeah, it might might sound difficult to I mean, one should have observed some effect of a massless neutrino, but in fact, the experiment doesn't constrain that.
But there have to be some consequence somewhere. I mean, you haven't seen what I mean, it's an important thing in your model. Have you looked at a small gun that is in which this massless neutrino is important? Because it's a part of the model, as far as I can see.
Yes. You can think this way. For almost since the standard model has been established, the neutrinos have been thought all along to be massless, and we didn't expect to see any special consequence regarding that. The fact that the other neutrinos are not massless are indicated in the oscillation experiments. But the oscillation experiments themselves have no problem with one of the neutrinos being massless. So it's different, for instance, if you have a scalar field which is massless, this would be very problematic because you would have a long-range interaction because scalars, gauge fields mediate interactions, long-range interactions. Neutrinos, being fermions, I mean, I think we are more safe in this sense. So I don't think that any other consequence besides the ones that were established by neutrino oscillation experiments would be observable concerning.
Wouldn't you have extra symmetry if one of the neutrino mass would go to zero?
No, it is not necessary symmetry. For instance, you can here we assume just two generations of right-handed neutrinos. Okay, so maybe I'm not 100% sure of that, but maybe if we assume three generations of right-handed neutrinos, and one of the right-handed neutrinos is very, very heavy, this extremely heavy right-handed neutrino can cause the lightest neutrino to have a very small mass. So in the limit of one of these right-handed neutrinos, the mass going to infinity, you have a limit of a massless neutrino. So I think that can be understood more or less in this sense. I don't think a symmetry is.
No, there is no symmetry restoring in this limit, in the limit of one of neutrino mass goes to 0.
Yeah, I don't think so.
Because there are other neutrinos with masses. If there would be only one neutrino, then masslessness would lead to U1 extra symmetry, right, of lepton number. But there are other neutrinos with the masses. So one neutrino massless, no impact on phenomenology, makes no visible impact.
Hi, may I know how many NR are there here? Like the right-handed neutrino NR? There are 2 or 3.
Yeah, I'm sorry, can you say it again?
How many right-handed neutrinos are there here? NR? How many generations of N?
Two generations.
So one active light neutrino being massless is an artifact of that, right? I mean, had you taken
Yeah.
3 right-handed neutrinos, then all the 3 light active neutrinos would have been massive.
Yes, that's true.
So that's also an artifact of taking 2 right-handed neutrinos, because
Yeah,
for the
of course.
yeah.
Mhm. Yeah, of course. This is an artifact of this assumption, which is a simplifying assumption. It makes the model more economic, but no problem if we include another right-handed neutrino, another generation. We will have ultra-massive light neutrinos.
I would like to comment that, for example, if one considers an extension of the fermionic sector by adding 3 like-handed Majorana neutrino instead of 2, it seems to me that the phenomenology will be very similar in what concerns the relation, dark matter, electron-muon conversion. It seems to me that the only difference will be in the neutrinoless beta decay. Maybe there will be a slightly different prediction for the effective Majorana neutrino mass parameter, or slightly different for the parameter space consistent with the neutrinoless beta decay. But at the end of the day, I think the general conclusion will be almost the same. Just only different will be in this neutrinoless beta decay.
Yes, I think this is really the place in which the lightest neutrino mass really have an impact. Because if you look at this plot, in the x-axis, we have the lightest neutrino mass. So depending on its value, we can have very, very small, I mean, this region goes down here. So we can have a very suppressed effective Majorana mass. But if I think this is an optimistic scenario in which one of the neutrinos is massless, because it puts a lower bound on this observable. So the experiments eventually can reach the full region if one of the neutrinos are massless. If not, depending on the specific combination of masses and phases, we can be in this region here, which the experiments might not be possible to probe. So, but yeah, that's the main place where I would expect an effect of this massless neutrino.
See. More questions from the audience? If there are no more questions, we thank Tessio again for the excellent talk and very complete talk.
Yeah.
Thank you very much,
Thank you,
Tessio.
Tessio. Yeah, thank you.
Thank you all. It was a pleasure.
Thank you.
Thank you.
Thank you so much. Have a nice afternoon, all of you, and see you at the next seminar. Bye. Thank you so much, Tessio.
Thank you. Bye-bye.
Bye. Right.